lectures of spring 2017. My name is Liam McAllister, and I'm a professor here in the physics department at Cornell. Before introducing today's distinguished lecturer, let me briefly describe the life and achievements of Hans Bethe, whom we honor with this lecture series. Hans Bethe was one of the leading scientists of the 20th century. He was born in Strasbourg in 1906, survived tuberculosis as a young boy, and began his study of theoretical physics at the age of 20 with Arnold Sommerfeld in Munich. Quantum mechanics was just then beginning to be understood, and Bethe made seminal contributions to understanding quantum phenomena in material systems, including crystals and metals. With the rise of the Nazis in 1933, Bethe was dismissed from his professorial position because his mother was Jewish. He went to England, lecturing for a year at the University of Manchester, and then came to Cornell as an assistant professor in 1935 for a yearly salary of $3,000. He was pursued at the time by many other universities. As he told his mother, "I'm about the leading theoretician in America. That does not mean the best. Wigner is certainly better, and Oppenheimer and Teller are probably just as good. But I do more and talk more, and that counts too." But he didn't just talk. In 1938, Bethe was the first person to understand how the sun shines. For his landmark work on nuclear fusion in the sun, he would eventually receive the Nobel Prize in Physics in 1967. With the outbreak of the Second World War, Bethe directed his mind to the war effort, beginning with radar. Oppenheimer then appointed him the director of the theoretical division at Los Alamos, where he played a critical role in the Manhattan Project. In the post-war period, he was a leading voice for arms control, disarmament, and the peaceful use of nuclear energy, and he was an advisor to Presidents Eisenhower, Kennedy, and Johnson. Bethe's scientific career lasted for more than 70 years. At the age of 85, he solved the famous solar neutrino problem. And at the age of 90, he calculated the rate of mergers of black holes and neutron stars to determine whether it would be possible to detect gravitational waves from their in-spirals. To quote our own Professor Kurt Gottfried, his intellectual output was on a scale that you would have considered impossible had he not actually existed. The Bethe Lecture Series was created in 1977 to honor Bethe's extraordinary contributions to physics at Cornell, and over 4 decades it has brought many of the world's most eminent physicists to lecture here. So now it's my great pleasure to introduce Professor Josh Freeman, who is a distinguished scientist in the theoretical astrophysics group at Fermilab, and also professor of astronomy and astrophysics at the University of Chicago. Professor Freeman received his BS in physics from Stanford University in 1981, and his PhD in physics from the University of Chicago in 1985. After a postdoctoral position at SLAC, he joined the staff at Fermilab in 1988. His research interests include theoretical and observational cosmology from the beginning of the universe to supernovae, dark matter, and dark energy. Early in his career, he made foundational contributions to the study of cosmic inflation. In the last 20 years, he has pioneered the theory and measurement of the distribution of galaxies in the universe. He's a founder and current director and spokesperson of the Dark Energy Survey, a collaboration of 400 scientists from 7 countries who are working to map the universe. He's a fellow of the American Physical Society and has been elected a member of the American Academy of Arts and Sciences. Please join me in giving a warm welcome to Professor Freeman.
Thanks, Liam. It's a real pleasure to be here. I've really enjoyed my visit these last few days. It's a wonderful department, wonderful people here. And it's a real honor to be here giving one of the Hans Bethe lectures. As Liam mentioned, Bethe was really one of the giants of 20th century science, a pioneer of nuclear astrophysics, a real man of science and a real humanist. It's also, we were talking about this at dinner. You can tell that Bethe was brilliant because most of us, our eyes are in the upper half of our heads. Bethe is like, his eyes are like right in the middle of his head, right? There's a lot of brain up there. So it's no wonder that he was really a giant of 20th century physics. So what I would like to talk to you about today is the dark universe. something I think Beta really would have appreciated, and some of our understanding of the dark universe and how we're going about trying to improve our understanding of it. But to get into the subject, I want to give you sort of a review of some of the basic things that we now understand about the universe, about cosmology, and things that I think every educated person in the world should know. So for some of you, these will be quite familiar. For others of you, these may be less familiar. So forgive me if I spend some time going through some of these basic facts, because I want to make sure we're all sort of on the same level playing field. And this is going to be part of my theme for the talk, is sort of these basic facts that I think everyone should know. So first basic fact about the universe is that it's very old. So how old is the universe? Any? Just shout out a quick guess. Anyone?
10 billion years.
10 billion years, close enough. 13.8 billion years old. How do we know the universe is so old? Well, it contains a lot of old things in it. So we know it's at least older than Donald Trump, so it's more than 70 years. But in fact, our Earth is 4.5 billion years old. We know that from radioactivity. Our sun, the star that gives us energy, is about 5 billion years old. The oldest stars in our galaxy that we've observed are on the order of 13 billion years old. And then we have finally, ultimately, measurements of cosmic microwave background radiation that really pin it down to 13.8 billion years old. So here's an image of a cluster of stars in our own galaxy. It comes from the telescope I'm going to be talking about later, Omega Centaurus, and this contains some of the oldest stars that we know of, around 13 billion years old. So that's the first fact. The universe is very old. Second basic fact about the universe is that it's really, really big. I'm not going to ask for an answer here, but this is about, this is the farthest objects that we can see in the universe. So we know the universe must be at least that big, because it contains objects that we can see that are this many miles away. So this is a 1 followed by, I don't know how many 0 miles that is. So obviously miles is not a good unit to use for astronomy, because we just can't keep track of all these zeros. So instead we use distances that are larger, for example, light years. So just to remind you, light travels at 186,000 miles per second. So in 1 year, light travels about 6 trillion miles. So that defines a light year, 6 trillion miles. And so this number of miles is billions of light years. So the most distant objects we see in the universe are this far away, so we know the universe must be at least that big. And for scale, our sun is about 8 light minutes away. It takes 8 minutes for light to reach us from the sun. The nearest other stars are a few light years away, just to get a sense of scale. So third basic fact is the universe contains, the visible universe that we can see, contains billions of galaxies. So I'm going to spend a little bit of time talking about galaxies. So this is a picture taken in Chile at the observatory we use that I'll be talking about. Here's the telescope we use. And this is a picture with a small digital camera. But if you let your eyes adapt, dark adapt long enough, you see something close to this with the naked eyes when you're out there. And what you're seeing in this picture are actually 3 galaxies. This galaxy here is our own galaxy. That's the Milky Way galaxy. It's the plane of stars that we live in. But then there are 2 other galaxies you can see with the naked eye from the southern hemisphere, the large and the small Magellanic Clouds. Unfortunately, living as we do in the northern hemisphere, there are no galaxies nearby enough that are easily visible with the naked eye. Sometimes you can barely make out Andromeda. But if you ever do go or are from the southern hemisphere, I urge you to go out away from city lights on a dark night with relatively little moon. If it's clear enough and you let your eyes adapt, you'll see these big clouds. Those are the Magellanic Clouds. Those are 2 galaxies orbiting our own Milky Way. So typical galaxies might look like this. This is what our Milky Way galaxy might look like if we could travel 1 million light years away and look back at it. They're about tens of thousands of light years across. They contain typically billions of stars. And they rotate, this one at least, and many galaxies rotate around their centers with a period of about a few hundred million years. And all the images I'm showing here were taken with the camera I'll be talking about later. So here's another galaxy, a sort of spiral-shaped galaxy in the constellation Sculptor. There's so again, there's billions of galaxies, so we'll just go through these one at a time. Okay, we're up to 3. Let's see, how long do we have here? I'm not going to show you all. Okay, so let's moving up from galaxies. So one thing you notice when you take pictures of the sky of galaxies is the galaxies are not just randomly placed on the sky. They live in and are shaped by a variety of environments and have proximity to, they tend to lie near other galaxies with which, like my teenage daughters, they occasionally interact. So you find pairs of galaxies, groups of galaxies, clusters with tens to hundreds of galaxies, and even larger scale structures. So that tells us there's kind of a hierarchy of structure in the universe. So here's an example. Well, right here in the lower part of this picture, you see a bunch of galaxies which are in a group of galaxies. They're all more or less at the same distance, more in relative nearby each other in space. Here's another example here of a cluster of galaxies. These galaxies here are all relatively nearby each other, cosmologically speaking. So the next scale up is clusters of galaxies. This is a picture of a famous cluster of galaxies called the Coma Cluster. Clusters have sizes of order of 1 million light years across or so, and a mass of order of quadrillion times the mass of the sun, so 1,000 trillion. And again, they contain tens to hundreds to thousands of galaxies within them. And this Coma Cluster is particularly interesting because it was studied by this astronomer, Fritz Zwicky. Zwicky was, as you can just tell by this picture, he was sort of an interesting personality, a bit of a curmudgeon, but he was a pioneer of many important concepts in astronomy and astrophysics. He was a pioneer of modern sky surveys. He was the person who really discovered dark matter and worked out notions about neutron stars, supernovae, etc. And in the 1930s, Zwicky studied the motions of the galaxies within the Coma Cluster. So he could measure the motions of these galaxies. And what he found was that these galaxies in Coma were moving around much more rapidly than you would have expected, given the amount of galaxies in that cluster. They were moving with speeds of order 1,000 kilometers per second relative to each other. And if you think about it, if you have a system of objects which are moving rapidly and it's staying bound together, there must be a lot of mass holding those objects together. Otherwise, they would have just flown out into empty space. And if you add up the amount of mass that we knew was in those galaxies, it didn't add up to enough mass to keep galaxies that were moving that fast from moving out into empty space. So the question was, why is Coma still there? Why didn't it just disperse because these galaxies were moving so rapidly? And what Zwicky hypothesized was that there must be some additional mass there which exerts a gravitational force that's keeping the galaxies within the Coma Cluster from flying off. And he called this dark matter. And in fact, we now know that clusters of galaxies are mostly made of dark matter. That picture I showed of galaxies was really just like the sprinkles on this massive ice cream cone of dark matter. And we know the dark matter is there because it must be exerting this gravitational pull on the galaxies that we do see. We now have abundant evidence that these clusters are filled with dark matter. One way we do that is using Einstein's theory of general relativity. This was Einstein on one of his better hair days. And Einstein taught us that matter and energy curve space-time, and that everything, including light, moves along paths in this curved space-time. And so we think of an object like a star exerting gravity by curving the space-time around it, and then other objects moving in that curved space-time. And one of the consequences of that is that if I have a massive system like a cluster of galaxies, and I look at a more distant galaxy, the light from that distant galaxy will get bent by the gravitational field, the distortion of space-time, by this cluster of galaxies. And so the light won't travel to us on straight lines, it will travel on these curved paths. They'll be distorted, and that means that the images of this distant galaxy will be distorted compared to what it otherwise would have looked like. And that, in fact, has now been seen, really for the last 30 years, with images like this from the Hubble Space Telescope. So what we're seeing is these objects here are galaxies in a cluster of galaxies that's called Abell 2218. These look like ordinary typical galaxies, but then you see these things, these very wispy, very extended objects. Those are images of galaxies that are behind the cluster, whose light has been distorted as it passes through and around the cluster, and so they end up as these very extended arcs. And so whenever you see these arcs, and they have this characteristic tangential pattern, that's the indication that the light is being gravitationally lensed. And we can use those images to actually reconstruct what the distribution of mass is in that cluster of galaxies. And so you find this sort of funny-shaped mass distribution. And it has two basic components. These very sharp, spiky things, that's the mass associated with individual galaxies in that cluster of galaxies. But then you also see this overall hump, this kind of mountain here. And that's the dark matter, which is more smoothly distributed. And we call that a halo of dark matter. And so this is directly telling us that most of the mass in this cluster is in this smooth, relatively smoother component of dark matter. Skip forward to the 1970s, and astronomers were studying the dynamics of individual galaxies. This is a famous one, M33. It rotates about its center. And by studying the rotation speeds of the stars in that galaxy, we can also understand something about its structure. The real pioneer in this area was Vera Rubin, who just passed away last December. And in fact, I just learned that she was a master's student of Hans Bethe when she was here at Cornell. So she and her colleagues studied the rotational motions of these galaxies. So this is one of the galaxies they studied, M33, velocity as a function of distance from the center of that galaxy, velocity of the stars. And what they expected was that the velocity would increase, but then gradually fall off. Because most of the stars are here, and you would expect the gravitational effect of those stars to weaken as you go out. And so you would expect this kind of rotation speed as a function of distance. And this is the kind of rotation speed you get, say, for planets in our solar system. Most of the mass in our solar system is in the sun, and the rotation speeds of outer planets falls off as you go farther and farther from the sun. But what Rubin and her colleagues instead found was that the rotation speed of stars kept increasing and sort of flattened out as you went to larger distances from the center of these galaxies. And these rotation speeds were much, much larger than you can explain from the gravity of just the stars in that galaxy. So again, there must be something else exerting a gravitational pull on those stars to keep them in their orbits, otherwise they would have spun out into empty space. And again, that was the evidence for dark matter. So again, now applying the same logic from clusters to galaxies, there's something in galaxies that's holding the stars into their orbits. Again, we can attribute to dark matter. Again, galaxies that we now know are mostly made of dark matter. The stars we see in those images are really just like the sprinkles on top of this much more massive halo of dark matter. And this picture now holds together remarkably well. And so in fact, here's an example of gravitational lensing, now not by a cluster of galaxies, but by an individual galaxy. So here's a galaxy relatively nearby to us. This image here is the highly gravitationally lensed image of a more distant galaxy, the light of which is being bent so dramatically by this foreground galaxy that the image of this background galaxy, which would otherwise look something like this, instead looks almost like a perfect ring. And again, this gives us information about the mass of these galaxies and tells us that they're mostly dark matter. Yeah?
The one that goes around like that, does that mean it's farther than the one on the right?
It's either farther or it's just closer to the line of sight of this galaxy, so the light is getting bent much more. This galaxy may not be as far as that one, so I don't know offhand, or it may just be far enough from the line of sight here that the light rays from this one are only slightly bent.
And one more thing,
Yeah.
this is going to sound really dumb, I'm really sorry, but you know, different galaxies are smaller and bigger. Is that because there's, how do we know how many solar systems are in a galaxy? Do we know that?
Well, we know how many stars are in these galaxies, roughly. There's, you know, in this kind of galaxy, there's billions of stars, and most of those probably have planets around them.
And how many stars are in the Milky Way?
About 10 billion or so, give or take.
Thank you.
Yeah. Okay, I just want to do one more example of this gravitational lensing. We can also do that, measure that lensing effect statistically. We can study the shapes of galaxies behind foreground galaxies. And we again conclude that almost all galaxies that we see, or actually all galaxies that we see, have these sort of extended halos of dark matter. And so we published some results on this back in the late 90s, again showing that statistically, sort of in general, using samples now of millions of galaxies, we come to the same conclusion that they're embedded in these halos of dark matter. Personally, I was much more interested in the article on prehistoric fashion that appeared in the same part of the New York Times. Okay, so we know dark matter is there. It's the dominant stuff in galaxies and clusters in galaxies. The question is, what is the dark matter? What's it made of? Your first guess would be, okay, we know what matter is made of. It's made of atoms, which is nuclei and electrons, or more fundamentally protons and neutrons and electrons, or even if you go down to smaller scales, you get down to quarks. So you might guess, okay, it must be the dark matter must be in some form of atoms that just doesn't shine very much, doesn't emit much light. And in fact, that was one hypothesis. But we now know that there simply aren't enough atoms in the universe to make up all the dark matter that we see in these systems. So you can imagine hiding quite a bit of the atoms into some kind of faint stars or planets that don't really shine, you know, ice balls or dust or something. But there simply are not enough atoms in the universe to account for all the dark matter that we are inferring in these systems. So the dark matter must be made of something other than atoms. And our best guess is that it's a new kind of elementary particle that's not part of our standard model of elementary particles that we've never seen before. So one hypothesis is that dark matter could be what we call a weakly interacting massive particle, WIMP for short. And the idea is that our galaxy and other galaxies would be made up of these just very large numbers of these dark matter particles continually swarming around through the galaxy. If that's the case, then occasionally one of those dark matter particles would interact with the nuclei if I make a big enough detector and put it deep underground to shield it from other things. You might imagine that one of these dark matter particles might collide with the nucleus in a detector, jiggle this nucleus a little bit, and enable me to detect that particle. And again, we have to hypothesize that these particles are weakly interacting. That means there are dark matter particles continually passing through this room, every second passing through your body. You don't notice it because they simply are not interacting. They're going straight through you. But for every now and then, one of these dark matter particles might collide with the nucleus, jiggle it a little bit, deposit a small amount of energy, which we could pick up with a very sensitive detector. So physicists around the world have mounted experiments to search for these weakly interacting massive particles. They build very precise detectors. They often cool them down to very low temperatures, put them deep underground, searching for these dark matter, these WIMPs coming from the halo of our galaxy. So far, there's been no definitive evidence for their existence, but we're continuing to search. A second possibility for finding dark matter is we might actually produce it. This is the Large Hadron Collider operating in Switzerland, in Geneva. This is where the famous Higgs boson was discovered in 2012. And the hope is that by bashing these protons together with high enough energies, we may start to produce some of these dark matter particles. Again, it hasn't happened yet, but there's still the possibility that it will. A third technique for trying to look for dark matter is to use the fact that if these weakly interacting particles are the dark matter, we expect there to be both particles and antiparticles. Those particles, if they're in a dense enough environment, will annihilate with each other and eventually produce things we can see, like high-energy gamma rays, very intense light rays. And so there's, NASA has the Fermi satellite orbiting the Earth, which can detect gamma rays. And so one possibility is that by looking either at the center of our galaxy or at the centers of nearby dwarf galaxies, the Fermi satellite may detect gamma rays coming from dark matter annihilation. Again, it hasn't yet been seen, but we will continue the hunt. Okay, so that was dark matter. Fourth basic fact about the universe is that the universe is expanding. So let's talk about that a bit. The person who really gets the credit for that is this person, Edwin Hubble. He was a graduate of the University of Chicago, studied law, amateur boxer, amateur basketball player, and professional astronomer. And Hubble has a number of really critical discoveries to his credit. He's the one who proved that these spiral nebulae, some of those images I showed, are actually other galaxies outside of our own Milky Way. He discovered the expanding universe, and he also did important work cataloging galaxies. So here's a picture of Hubble using the Palomar 48-inch telescope, which he and others used for sky surveys. Sorry? I think this is the 200-inch. Yeah. I'll check that. Anyway, this is Hubble with the telescope. There's one problem with this picture, of course, which is that he left the lights on in the dome. So I don't think he's actually looking at much there. Normally we turn the lights off when we want to take pictures of the universe. This is Hubble in an earlier phase of his existence, when he was an undergraduate at the University of Chicago and a member of the famous 1909 National Championship basketball team. Of course, the University of Chicago is well known as a NCAA basketball powerhouse. For many years, I thought it was quite interesting that this was also 1 year after the Cubs had last won the World Series. But that's no longer true. The other thing that strikes me about this is, looking, first of all, it's a small basketball team, right? There are only, 7 people on it. And if you look at some of these guys, basketball looks like it was a pretty rough sport back then. Anyway, in the equivalent of March Madness in 1909, the University of Chicago defeated their arch rivals, Indiana, by the very high score of 18-12. It was actually in January back then, it wasn't in March. And here's the basketball that was used in that important game, sitting within the space shuttle. It was taken up by astronaut John Grunsfeld, and in the background of this picture here is the Hubble Space Telescope that they were servicing. Okay, so here's one way to think of the expanding universe. It's basically everything is getting farther away from everything else. And if you can think of it as a movie in this way, this has a number of limitations, but it's one way to picture it. And if I run this movie backwards, everything would be on top of everything else 13.8 billion years ago. And that's the moment we call the Big Bang. A few things to point out about this picture. Here's the universe at one time, here's the universe at a later time. These two things can be stand-ins for galaxies. So at a later time, they're farther apart from each other than an earlier time. That's reflecting the expansion. And to set the scale, a galaxy that's currently 100 million light years away from us is receding from us due to the expanding universe at about 2,000 miles per second. It's also important to know that galaxies themselves are not expanding. So the Milky Way galaxy we think is stable, it's gravitationally bound. So it's the distances, galaxies are getting further apart from each other, but they themselves are not expanding. They're bound together by gravity. A few other points to make about the expanding universe. Because that picture can be misleading. It looks like the universe is an expanding balloon, then there must have been some center. We don't really think the universe has a center or an edge, at least not that we can see. It looks the same everywhere, and isn't expanding into some pre-existing empty space. Instead, the expansion is happening everywhere. And so a better analogy for this might be, imagine you make a raisin bread, but that's infinitely large. You put it in the oven with some yeast. It expands. The raisins will move away from each other. But there's no, if it's infinite, there's no center to that raisin bread. The other point to note is that you know that as a gas expands, it generally tends to cool, become less dense. And if you run it backwards, a contracting gas becomes more dense and hotter. So today the universe is relatively cold. It's 3 degrees above absolute zero and very diffuse. But going back towards the Big Bang, it was much hotter and much denser. Okay, and so this is actually a picture taken of the early universe when it was only about 380,000 years old. This is a map of the cosmic microwave background radiation taken by the Planck satellite. And these red and blue spots are slightly hotter and slightly colder than this average that's just a little below 3 degrees above absolute zero. And the differences here have been magnified greatly. This point is only 0.00001 hotter than average. This point is only 0.00001 cooler than the average. So the temperature differences are very tiny. The first approximation, the universe has the same temperature everywhere. So the universe looks very smooth, very isotropic around us. Today, though, when we look at the map, when we look at study the distribution of structure in the universe, so this is a map of the distribution of galaxies from the 2-mass infrared survey, the universe is much lumpier. We see much larger fluctuations in the density of matter today than there was when the universe was only 380,000 years old. So our understanding of this is that initially the universe, moments after the Big Bang, had very small amplitude ripples or fluctuations in its density. But then over time, those fluctuations grew, became more and more larger and larger fluctuations, and eventually collapsed to form structures that hosted things like galaxies. And our picture of how that forms is through gravitational instability. So here's a simulation on a computer of how we think this happens, starting from nearly homogeneous, uniform distribution of matter at early times, and then simply by the action of gravity, becoming a very clumpy universe at late times. And the only thing that really went into this simulation was dark matter particles and gravity. They didn't even bother to put in atoms, the sprinkles on the ice cream, to make this simulation. And it looks remarkably like the structure we see in the universe today. So again, our picture is that there was this Big Bang nearly 14 billion years ago, an early epoch of what we call inflation that led to the seeds, these initial tiny fluctuations in the density of the universe that was imprinted on the cosmic microwave background 400,000 years later. And then since then, gravity has been the engine acting on dark matter to produce the structure we see in these galaxy surveys today. So a natural question to ask is, okay, we know the universe is expanding. We've known that since the 1920s, the work of Hubble and others. You can naturally ask, does the expansion of the universe change over time? And your answer would be, so let's look at a particular galaxy. It's receding away from us due to the expanding universe. Is it going to have the same speed tomorrow that it has today? Or will it be slower, moving slightly slower, or moving slightly faster than it is today? And our naive expectation is that, well, the gravity of our galaxy, the Milky Way, is pulling on that distant galaxy. So I would expect if it's moving away from us, because we're tugging on it, that tomorrow it would be moving slightly more slowly than it is today. And that means we expected the expansion of the universe, all other things being equal, to be slowing down over time. And yet, in the late 1990s, 2 teams of astronomers studying distant type 1a supernovae, in fact found the universe, the expansion wasn't slowing down, it was speeding up. And for this discovery, they were awarded the Nobel Prize in 2011. So I want to spend some time talking about this issue. So what they did is they studied supernovae. So here's a relatively nearby galaxy of billions of stars. There's a lot of dust in this particular galaxy. And this is a particular picture of a supernova, a star that exploded in this galaxy. And Hans Bethe made a lot of important contributions to our understanding of the physics of how supernovae explode, the nuclear and astrophysics. So a few weeks before this picture was taken, you wouldn't have seen any star here. And a few months after this, well, a few years after this picture was taken, you wouldn't have seen any star here either. But yet, over the course of about 3 weeks, the star exploded, and about 3 weeks later became as bright, nearly as bright, as an entire galaxy of billions of stars. So that's quite impressive. And in fact, these particular kinds of supernovae all have nearly the same brightness when they reach their maximum brightness. They're sort of like 100-watt light bulbs with a very small differences between the wattages of them. And so that means we can use them as standard candles to try to understand the expanding universe. So here's a gallery of nearly 500 of these supernovae that we discovered about 10, 12 years ago in a different survey we did. So each of these images is centered on a supernova that exploded, and then the fuzzy thing near it is the galaxy in which that star exploded. And again, by making these images and observing them every few days over the course of months, you can see these explosions happen, chart their brightness over time, and use them to determine how far away they are. So these particular supernovae we call type 1a supernovae, we think are white dwarf stars that approach or maybe reach a certain maximum mass and then become unstable and explode. That could happen if you have two white dwarfs in a binary system that eventually in-spiral and collide and merge. Or it could be if you have a white dwarf star with another ordinary star nearby it, the white dwarf star would pull mass gravitationally from that companion, eventually reach its maximum mass, and again explode. Skip that. So, basically what we found was that from these supernovae observations, we now know that the universe, in its early phases, the universe was expanding and in fact was slowing down for about the first 8, 9, 10 billion years of cosmic history. But then a few billion years ago, the universe started speeding up. The expansion went from slowing to speeding. And this is strange because if you think about everyday experience, whenever you've thrown anything up in the air, as soon as it leaves your hand, it's slowing down, right? Because it's being accelerated towards the center of the Earth. So the Earth is tugging on it, it's decelerating it, and eventually, because none of us can throw that hard enough, eventually it falls back down to Earth. But imagine instead that one time you threw something up, it initially left your hand, initially started slowing down, but then before it reached the top of its trajectory, it suddenly sped up and rocketed out of the atmosphere. That would be strange. No one's ever seen that happen before. And yet that's what we think the universe is doing. First 8 billion years or so, it was slowing down, and then sped up. So this is bizarre. It's not something we've experienced in our everyday life, so it needs some kind of physical explanation. And we've come up with two basic kinds of explanation for what could be causing the universe to speed up. One possibility is that the universe is filled with this new stuff that we call dark energy, which has the property that, unlike all other forms of matter, it exerts a kind of gravitational repulsive force when it's there. So it doesn't cause things to attract each other, but to repel. And our picture is that about 70% of the total mass energy in the universe would be in the form of this dark energy, about 25% dark matter, and about 5% made of atoms, the stuff we're made of. The second possibility is that there isn't dark energy, but there's something strange going on with our understanding of gravity. Our understanding of gravity comes from Einstein. It worked very well in the solar system. It explains those beautiful lensed galaxies. But maybe when we get to cosmic scales, Einstein just wasn't right. Maybe he was playing a joke on us. And we have to replace his theory of gravity with some new theory. And so we would like to figure out which of these is the right explanation. So this is sort of our current, this is fact number 6. Our current picture, assuming it's dark energy, is that 95% of the universe is dark. So here we are, 5% made of visible matter, the stuff made of atoms, that's just the tip of the iceberg. 25% dark matter, that's the stuff that we think is responsible, the gravity of dark matter is responsible for the formation of galaxies and holds them together. And dark energy is the stuff that started pushing galaxies away from each other, causing the universe to speed up a few billion years ago. So, what is dark energy? The short answer is we have no clue. It's a component with negative pressure, which is bizarre, and we can come back to that later. But the interesting thing is that the most conservative idea about what dark energy is that it's literally nothing. And what I mean by that is that the most conservative picture is that dark energy is actually the energy of empty space. So in classical physics, if I have some region which has no particles in it, so if I hooked a vacuum hose up to this bottle, sucked out all the water, sucked out all the air, shielded it from cosmic rays and dark matter, there would just be empty space there. In classical physics, there would be no energy in it either. But according to quantum theory, even if you have no real particles there, because of the Heisenberg uncertainty principle, there would still be energy there associated with the vacuum. If you calculate in quantum physics what that energy should be, you get a rather embarrassing number, which is infinity. Even if you put in sort of a fudge to make the answer finite, the reasonable numbers to put in for that fudge factor still give you an answer that's 120 orders of magnitude too large. Now, some of you are students. You're used to doing homework problems. Occasionally, you'll make an error by a factor of a half, or a factor of 2, factor of 3. It's really hard to make an error by 120 orders of magnitude, right? You really have to screw up, and yet that's what our current understanding of physics tells us. So there clearly must be something going on here. Whether this has anything to do with this conservative hypothesis, we have no clue. So still, the conservative hypothesis is that dark energy is the energy of the vacuum, empty space. We don't know why it has this particular value it has. And there are other more speculative ideas. Perhaps dark energy is associated with a new kind of particle, a much lighter cousin of the Higgs boson that was discovered a few years ago. So we would like to know to try to answer these questions. Why is dark energy important? Well, dark energy is 70% of the universe today, and as the universe evolves, dark energy becomes more and more important. So whatever its nature is, it's going to determine the future evolution of our universe. So if we want to have any hope of figuring out where the universe is going, we need to figure out the nature of this dark energy, or at least try to. And it turns out that by making surveys of the universe, we can try to get at clues as to what this dark energy is. So that's going to be what I'm going to talk about for the remainder of the talk, is how we probe, how we're trying to understand this dark energy and the acceleration of the universe. So the project I'm involved in is called the Dark Energy Survey. So you can see it was designed to try to get at this question. And we're basically making a big map of the universe using this camera on this telescope down in Chile to try to understand the history of cosmic expansion and the growth of this large-scale structure that we saw the movie of before, to try to pin down the nature of dark energy and whatever's causing the universe to speed up. In detail, what we're doing is basically taking snapshots of about 300 million galaxies that are spread over about 1/8 of the sky that we can see down in Chile. And we're also doing a survey where we revisit a few particular points on the sky to discover these supernovae, since that also is a good way to probe dark energy. And we'll discover about 3,000 of these supernovae. So our survey started about 4 years ago. It's generously supported by the U.S. funding agencies, the Department of Energy, the National Science Foundation, and we have a number of foreign and U.S. institutional partners as well that have all come together to make this project. Let me see that. So to make a project like this work, you need a big team. So as I mentioned, about 400 scientists. These are the institutions that we come from, many of them in the U.S. And this is the telescope we're using. I showed you a picture of this earlier. So this is at Cerro Tololo Inter-American Observatory. This is high in the, well, sort of in the foothills of the Andes Mountains of northern Chile. And on this site, there are a number of telescopes. The one we're using is this telescope here, the Victor Blanco 4-meter telescope. So if I go inside that dome, this is what it looks like looking from the top of the dome. Is Phoebe here? Phoebe, hey, good. This is Phoebe's dad, Klaus Sunshine, one of the people who really built the project. Klaus is a professor at Ohio State University, did important work on the project. He told me he would be here. If I then go inside the dome, this is what the telescope looks like. So it's got a mirror that's 4 meters across, that's here. And then our camera's up here, it's a kind of a foreshortened view. So light comes in from the universe, bounces off this mirror, goes up into this cylinder here, passes through 5 lenses, and then hits the focal plane of our camera. So this is what the camera actually looks like. And this is a little bit bigger than real size. It's a very big camera, 570 megapixels. That doesn't sound like too much. Your iPhone has probably 10, 12 megapixels. But these are really nice pixels. They're very sensitive, particularly to dark light. Unfortunately, there's no flash on this camera, so I don't know, $40 million and we couldn't get a flash. Anyway, we built this camera at Fermilab outside of Chicago and installed it on this telescope in 2012. And in fact, before we did that, we built a replica of the top end of the telescope. So here's the telescope. Here's the top end of the telescope. The mirror's down here. Here's our camera. Before we put it on the telescope, we built a replica of the top end of the telescope at the lab, at Fermilab outside Chicago. And that's because this telescope is, as I said, it's high in the Andes, it's a remote mountain site, it's an earthquake-prone region. Before we decided to take this all apart and put in this new $40 million instrument, we wanted to make real sure that we could do it all and that it would work without a hitch. So we built this thing we call the telescope simulator in order to test it all out before shipping it down to Chile. I mentioned there are 5 lenses in this camera. Here's the biggest lens here. It's just about 1 meter across. And also, we use some of the largest filters that have been produced for astronomy. These were produced by a Japanese company, Asahi, and remarkably, they were able to finish fabrication of these filters just a few months after the devastating tsunami of 2011 hit Japan. So with each image we take, we have a filter across the focal plane that only lets in light of a particular wavelength range. And then we come back to that same point in the sky and take images through other filters. So that gives us color information about all these galaxies, from blue to red. So this is what a typical raw image from the camera looks like. So each of these is one of these 2,000 by 4,000 pixel CCDs. There's 62 of them in total. 2 of them now don't work, so we're down to about 60. So you see images of galaxies here, you see a bunch of other stuff. And so part of what we have to do is process these images to get rid of artifacts associated with the camera to do science with it. This camera has a very wide field of view. If we were to point it at the moon, it would fully encompass the moon. So it's a very wide field camera compared to most astronomical cameras. We don't point it at the moon because the moon's way too bright. So here's one of the first images we took with the camera of the Fornax cluster of galaxies. This was back in September of 2012. And let me just play a little short video from that. So you can see the outlines of the CCDs here. And then we'll just zoom in on a few of the galaxies that are in this. Again, this is a cluster of galaxies that we were talking about earlier. And in particular, there's this very beautiful galaxy, NGC 1365, this beautiful spiral galaxy inside this cluster. Here's just a version of that in a slightly different color. So basically what we're doing in this survey is taking pictures. We're taking snapshots of the universe over and over and over again. Every year we take close to 20,000 pictures. Each of them, the exposure is about 90 seconds long. And then we stitch them together to make a picture of the entire sky. Here's a cluster of galaxies. So eventually, after 5 years, we will have made a map over this funny shaped region of the sky, 5,000 square degrees. That's about an eighth of the total sky. It's in the southern hemisphere, so we can look out into the southern portion of our own galaxy. And I just want to show another quick movie. So again, this is our footprint here on the sky. And I'm going to show you each one of these little things appearing is one of the images we took. The focal plane is roughly hexagonal shape, so that's why you see these little hexagons appearing. And basically every time we've taken an image somewhere in our footprint, you're seeing one of these things turn on. And we just keep doing that night after night after night, 105 nights a year for five years. And so we now have a full map over the whole footprint. We're continuing to take pictures to make them go deeper and deeper. And now we'll just zoom in, do a quick zoom in on one of the regions that we've observed so far, just to give you a sense of the dynamic range of this data set.
Are all those dots galaxies?
They're almost all galaxies. Some of them are stars, but most of them are galaxies. So this is like a star in our own galaxy, but all these things are other galaxies. Okay. So I mentioned one thing we're doing is, in addition to doing this very wide area survey, we're also looking for supernovae. So here's again an image from the camera, and we're now going to zoom in on just one of these little CCDs here, and now blow it up here. And then we'll blow up this tiny region here further, and you see a nice image of a spiral galaxy. And then we came back sometime later, took a picture of the same image, and you can see something has changed. In addition to writing appearing on the sky, you see that right near the center of this galaxy, right here, something appeared that wasn't there before. And then, very fortunately, God or someone puts an arrow and tells us that that's where it went off. No, actually, we put the arrows on later. So this is an example of a supernova that exploded in this galaxy in late 2013. So we go back and by just taking pictures of the same part of the sky over and over again, comparing them to previous pictures you took, you can discover these supernovae, measure their properties. Let me see if I'm going to have time. Yeah, okay. I mentioned this gravitational lensing effect where the light from distant galaxies gets bent on its way to us due to Einstein's theory of general relativity. So for most distant galaxies, like the picture I showed you before, most of the galaxies were not those very distorted, nearly ring-like shapes. Most of them looked pretty much like ordinary galaxies. And that's because for most lines of sight through the universe, the bending of the light rays on its way to us is very tiny. And so this is called weak gravitational lensing, where the light rays from distant galaxies just get slightly bent, leading to a slight distortion in those images. So when you look at any of those galaxies, you can't tell that it's been bent by gravity because it looks essentially just like an ordinary galaxy. But by looking at the shapes of galaxies nearby on the sky and sort of averaging them, you can look for this tiny bending effect, and that's called weak gravitational lensing. And in fact, we can use that to map out the dark matter in the universe. So this is from a simulation. The colors here are showing you these red regions are where there are clusters of galaxies, overdense region. The blue regions are underdense regions of the universe. And these little tick marks are showing you how much bending of distant galaxies would be due to this mass. So here, there's a big cluster of galaxies. You see this tangential shearing that we saw in those earlier Hubble images of galaxies. But even out here, where you're in an underdense region of the universe, there would still be a net shearing, a distortion of the images of distant galaxies. So we can use this technique to actually make a map of mass, mostly dark mass, in the universe over very large scales. So this is a map, the largest map of dark matter yet made, extending over hundreds of millions of light years using this light bending technique. So the dark regions, the dark red regions, are where there's more dark matter. The blue regions are where there's less dark matter. And by making these kinds of maps and studying their properties, we can try to learn about dark energy and cosmic acceleration. So this map that we made here and here, this is made based on only 3% of the data. This is data we took in 2012, before we even started the survey. This picture contains a few million galaxies. We're now analyzing a much larger set of data, covering about 1,000 square degrees on the sky, many millions of galaxies. And for comparison, the region I showed you before just fits in right there. So in the next couple of months, we're going to put out a bunch of publications analyzing this much larger data set, and then next year we'll publish results based on our full 5,000 square degrees of data. It turns out that this kind of survey, and this will be the last couple of things we'll talk about, is also useful for other things besides cosmology, or at least besides dark energy. So it turns out when you're making a large, deep map of the universe that hasn't been made before, you discover things that you weren't completely expecting. And this is an example of that. So again, this is the site, our telescope here. Here's the large and small Magellanic Clouds, our Milky Way galaxy over here. This is showing you the outline of the survey area that we've covered so far. And these red points are showing you the locations on the sky of brand new, very nearby galaxies that we discovered. These galaxies are in our own cosmic backyard. They're literally small little satellites of our own Milky Way galaxy that are so faint that they just hadn't been discovered by previous surveys. And in the last couple of years, we discovered 17 of these ultra-faint dwarf satellite galaxies. So this is what an image of one of them looks like. You can't really tell that there's a galaxy there, it just looks like a bunch of stars. This is where we isolate the stars that are just in that galaxy from the background of the much more numerous stars that are within the Milky Way. So it's obviously difficult to identify these things, but through specialized techniques, you can discover and map out and study these ultra-faint dwarf satellite galaxies. These nearby dwarf galaxies are very interesting for reasons that I alluded to earlier. Namely, these things are mostly dark matter. They're very rich in dark matter. So if there are dark matter WIMPs and anti-WIMPs in those galaxies, they will annihilate and give rise to gamma rays. So we asked the people who operate the Fermi satellite to look in their data in the direction of these dwarf galaxies to see if they saw any hint of gamma rays, and the answer is no. And so we can use that to say, okay, we can rule out certain models of dark matter based on the fact that we didn't see them annihilating in these dwarf galaxies. Final thing we've been spending some time looking at is coming even closer to home. The opposite extreme from dark energy is looking at objects in our own solar system. So here's, in the upper left, here's a picture of the inner part of our solar system, so the Sun, Mercury, Venus, Earth, Mars, asteroid belt, Jupiter. If we zoom out from that, then we get into the outer planets, Jupiter, Saturn, Uranus, Neptune, Pluto, and there's a band of objects out here called the Kuiper belt. If I zoom out from that and then there's this object out here called Sedna, which is a distant dwarf planet, even more distant than Pluto. Here's our solar system. Here's the orbit of Sedna. So it goes much further away from the sun than any of the standard planets we know about. And if I zoom out still further, here's the orbit of Sedna. In the very outer reaches of our solar system is this group of small bodies called the Oort cloud. And by studying these outer solar system objects, we can learn about the formation and history of our solar system. And so let me just, sorry. So one thing we can do is use the fact that some of these fields we observe every week or so. And so these are the trajectories of some of these distant outer solar system objects, so-called trans-Neptunian objects. And each of these little red tick marks is when we saw that object in our fields. And then a few days later we saw it move, and so we can map out the trajectories of these objects. So we've now discovered over 50 new trans-Neptunian objects, outer solar system objects, using this kind of methodology. And we expect to find many more. Some of you may have heard of this thing called Planet 9. So if we look at these outer solar system objects, here's Sedna, there's a bunch of other ones which all seem to have orbits that are kind of lined up with each other. That seems to be a bit improbable. And so some astronomers have hypothesized that there's a new planet way in the outer solar system whose orbit is affecting these bodies and kind of keeping them aligned together. And this is called Planet 9. It would be about 10 times the mass of the Earth, and would be way in the outer solar system. We've actually discovered a couple of these bodies whose orbits seem to be explained by this Planet 9. And so we're now engaged in looking for this Planet 9, this hypothesized ninth planet, since Pluto got demoted. And our best guess for where Planet 9 is on the sky is, in fact, right here, right in the center of the area that we're surveying. So we're looking hard for Planet 9 to see if it's there. We haven't yet found it, otherwise you would have heard about it. But we're going to keep looking. However, in the course of looking for things like Planet 9, we have found other distant planets. So here's one we found called UZ224. It's the second most distant known object in our solar system, 90 times farther away from the sun than the Earth. It takes about 1,000 years to go around the sun. And we found it by the fact that between these two images, it was something that had moved. And we've since measured how big this object is, and it's sort of just on the edge of being big enough to be a planet. Here's an artist's conception of what that planet looks like. This is drawn by Heather, who's 9 years old. So we haven't yet named this planet, so far it's just UZ224. I guess it's supposed to be named after a god. Sometimes you just take pretty pictures of other parts of the sky, so this is with our camera. Sometimes you take pictures of things that you weren't meaning to, so it just happened that this comet Lovejoy was in the path of where we wanted to observe on a particular night. We hadn't bothered to check that it was there, so we snapped a nice picture of it. So, to summarize, here's what I want you to take away from this hour. The universe is 13.8 billion years old. It's 95% dark. We think about 25% dark matter. There will be a quiz at the end of this. About 70% dark energy. It's filled with billions of galaxies that are each mostly made of dark matter. It's expanding from a Big Bang 13.8 billion years ago. And that expansion we now know is speeding up, likely due to dark energy or perhaps to something funny going on with gravity. And to understand this in greater detail, we're now embarked on a number of surveys, including the one I talked about, the Dark Energy Survey, to address this mystery and learn more about the evolution of the cosmos. We don't know the answer yet, so stay tuned, and we hope in the coming years to start giving some answers. So I'll stop with that and then play this little movie that one of our observers made when they went out to Chile. Thank you. I don't know how they got the music so simple. So that's the Milky Way setting. This is on a relatively cloudy night. It's usually not that cloudy night. So there's the Milky Way on the left, the imaginary clouds up in the middle. That beam on the left is actually a laser being shot out from another telescope on a nearby observatory. Here's inside the dome. This is obviously sped up. We're not that fast. You can see airplanes and stuff going overhead. And then the sun comes up. Yeah. Questions? Yeah.
In the survey, what was the reason you chose to map that particular area?
Okay, so the question is, why did we choose to map this particular area of the sky? Excellent question. So there are a couple of, right, so why are we looking here? So there's a couple of reasons. One is there's an area that I didn't have time to talk about, the far southern portion that's called SPT. That's a region of the sky which is being imaged looking at the microwave background from a telescope at the South Pole. So SPT stands for South Pole Telescope. And we wanted to be able to compare our data with their data. So we knew we need to be able to see the same part of the sky. That tells us we have to be in the southern hemisphere. And then you can just ask, okay, we want to cover that region, and we also want to be looking, so you know, our Milky Way is sort of a disk galaxy. It's got lots of stars and gas in it. So if we look sort of in directions, if we look in these directions here, we would be looking basically through the plane of our Milky Way. There's just too much stuff there. You can't really see outside galaxies. So we want to look in these regions that are sort of outside the plane of our galaxy. So that's this darker region here. And then basically you can just ask, okay, how much, you know, how do we cover this area most effectively? The other thing, this funny shaped thing here, which looks like sort of the turret of a tank, is because there's other surveys that were done from the northern hemisphere which had observed this part of the sky. We wanted to overlap with those and take advantage of some of the ancillary data. So that led to this sort of funny shape here. But it's basically we want to observe this part of the sky that's sort of out of the plane of the Milky Way that we can see from the southern hemisphere.
Yeah, so collecting all these pictures over many tens of years, how is that going to lead you to understanding dark energy?
Okay, good question. Thank you. So, let's say a little bit about that. Since you asked. Here. So there's basically four methods that taking these pictures are going to enable us to implement to probe dark energy. The easiest one is the supernova. That's the one that led to the discovery that the universe was speeding up in the first place. So we do that by just taking a portion of our time, and instead of looking over this whole 1/8 of the sky, we go back and every week look at a few small pieces of the sky, discover supernovae, use them as standard candles to map out the history of cosmic expansion. And by doing that more precisely, that will give us one handle on the effects of dark energy on that expansion. So previous supernova surveys have done tens to hundreds of supernovae. We're observing thousands of supernovae with higher data quality. So that's one of the techniques. And that uses this sort of what we call time domain survey. The other three techniques use this big wide area map that we're making. And they all rely on the fact that what dark energy does is to impact not only the expansion rate of the universe, but also the rate at which structure forms and evolves in the universe. So for example, here, what we're doing is simply taking a census of galaxy clusters. So we look in our map, and we identify all the places where we see clusters of galaxies. I showed you some images earlier, like the Coma Cluster, other clusters. They're pretty easy to identify. They're a bunch of sort of reddish galaxies all in a small portion of space. We can identify those. As I said, a cluster is really mostly made of dark matter. So that's giving us a census of these big halos of dark matter. How many of those dark halos you form is dependent on how fast the universe has been expanding and how dark energy has been affecting the expansion and the growth of structure. So by simply counting clusters of galaxies in some part of the sky, that also is giving us information on the properties of dark energy. Third technique is the one I talked a little bit about, weak lensing, measuring the shapes of these distant galaxies. They're slightly distorted, but that distortion is also determined by the mass, the clumpiness of the dark matter along the line of sight. That's what's jiggling these light paths around. And again, that degree of clumpiness is determined by how much dark energy there is and what its properties are. And then the fourth method is simply to go out and figure out where all these galaxies are, see how they're clustered together, and that also is sensitive to, if you like, this sort of cosmic tug of war between dark energy and gravity. And so we want to put all these techniques together in this one survey to make substantial improvements in understanding cosmic expansion and the growth of structure compared to what we've had with previous surveys.
So how did you get the percentages of dark matter and dark energy?
How do we get these percentages?
Yes.
Good question. So, right, so how do we know that it's 70% dark energy, 25% dark matter, for example? So there are a number of different ways we have of doing that. One is, as we vary the amounts of dark matter and dark energy, we vary the history of cosmic expansion. So for example, so dark matter is the stuff that makes the expansion slow down. It makes things clump together. But when the universe was mostly dark matter, so actually, I have a slide on that here. So here's a picture of roughly of the rate at which the universe has been expanding, starting from the Big Bang to today. And so this curve here is, if you like, sort of an indication of the sort of typical separation between two galaxies as a function of time. And so here's the Big Bang. Here's 1 billion years after the Big Bang, 9.5 billion years, and here we are today. And our picture is that early on, the expansion was, things were moving away from each other, so this curve was going up, but it was concave down, right? It was going slower than linear growth. And then at some point around 10 billion years ago, it started curving upward. That's when the universe started speeding up, started accelerating. So for the universe to be slowing down, it must be, most of the mass in the universe must be stuff that makes it slow down. That's dark matter. Once the universe starts speeding up, that's when dark energy must have become more plentiful than dark matter. And so this tells us that today the universe is mostly dark energy. Back then the universe is mostly dark matter. And once we understand the properties of dark matter and dark energy, how they change with time, we can then work out these ratios. So today I said dark energy is about 70%, dark matter is about 20%, atoms is about 4%. If I go back to this period where I just changed from slowing down to speeding up, that means I was just changing from being mostly dark matter to mostly dark energy, so they must have been closer to 50-50 at that point. And if I go back even further, we know that as the universe expands, dark matter becomes more dilute, but dark energy doesn't very much. So if I go back in time, That means dark matter was more dense. So back at this time, 1 billion years after the Big Bang, it was 84% dark matter, 15% atoms, and only 1% dark energy. So that ratio, the 70%, 20%, that's just today, we think. And that comes from a number of these sorts of measurements that I just mentioned. But we think going back in time, back before a few billion years ago, dark energy played very little role. It was mostly dark matter. And it's only in the last few billion years that dark energy has come to dominate. And if our understanding is correct, then as the universe keeps expanding, this ratio of dark energy to dark matter is going to get even bigger and bigger. So in the more distant future, it'll be 99% dark energy, only 1% dark matter. So this kind of particular inference is basically based on inferences about what we know so far about the rate at which the history of cosmic expansion. What we're trying now to do is measure this more precisely to understand not only these numbers, these percentages, but to learn more details about the properties of the dark energy itself.
One final question.
Yeah.
It's almost a philosophical question.
Okay.
Do you ever get the sense that you are importing the ether from the 1900s?
That we're doing what with the ether?
Importing nature to try to understand
Oh.
from the ether
Right.
before Einstein.
Right, so what you're referring to is that before Einstein, there was this hypothesis of an ether, a luminiferous ether, to explain observations of the speed of light. And so you might say, well, gee, aren't we doing the same thing here? 95% of the universe is dark. We've never seen it. Doesn't this just sound like we're just making things up? And that's a good question, and you should ask that. Of course, the answer is no, we're not making all this up. And I think the thing that the reason is because, let me tell a little story about that. So, 1998 is when these astronomers announced that they had discovered that the universe was speeding up. That was not the first time that astronomers had thought they had seen something like that. If you go back into the history of 20th century astronomy, there were a number of times when astronomers thought they discovered something like the accelerating universe. And basically, every time they did that, within a year or two, it was shown that they were wrong. They made some systematic error, some oversimplifying assumption. And so the evidence always went away very quickly. And so in those cases, you might have said, okay, they were sort of jumping the gun a bit. But we're now in a very different situation, right? We're now 20 years after the discovery of cosmic acceleration from supernovae. And we have information not only from the supernovae, but from the cosmic microwave background, from the clustering of galaxies, that all points to the same strange picture of a universe that looks like this. So it's not just one single observation that gives us this picture. We now have a whole interlocking web of observations, all of which are pointing to this picture. And as we make more and more observations, the data gets better and better, we understand it better, the errors get smaller and smaller. This picture gets stronger and stronger. And that's very different from what happened in the past, where we thought maybe we'd seen it and then it went away. So I would have said, maybe in 1998, you could have been a skeptic about this, and you might have said, well, look, they're just making all this stuff up. But we now have so many different lines of evidence. So dark matter, it's the observations of the motions of stars within galaxies, the motions of galaxies within clusters of galaxies, the bending of light from galaxies behind clusters, all pointing to the same thing. Dark energy is the brightness of these distant supernovae, it's the clustering of galaxies, it's the cosmic microwave background, again, all adding up to this. For this 5% visible matter, the pattern of those hot and cold spots in the microwave background points to this. So does the abundance of light nuclei in the universe, also points to this, that were cooked in 3 minutes after the Big Bang. So there's no longer, it's not just one little piece of evidence, it's many, many interlocking, mutually supporting pieces of evidence pointing to this picture. And that's very different from what was in the 20th century. It's very different from, the picture of the ether. And so I think we can't just, it's tempting to say, well, gee, it's all dark. You must be just sort of fudging and making this all up to explain what you see. But it's really the fact that we now have so many different lines of evidence that are getting stronger and stronger over time. We really, we can't ignore this anymore. I would like nothing better than to disprove that there's dark matter or dark energy. That's the other thing, is that there's sometimes this assumption that physicists just want to make things up and sort of go along. But physicists would like nothing better than to prove their colleagues wrong. And so a lot of people have looked hard at this and tried to find problems with it. And with any one little piece of evidence, yes, you can find there are errors that we need to do a better job on. But the fact that we have so many different lines of evidence pointing to this, it's hard to just dismiss this.
So on that note, before we thank Professor Freeman again, let me make an announcement. For those of you who RSVP'd, there will be a reception in the West Pavilion of PSB. But now let's thank Professor Freeman for a while.